Alkyl halides, nucleophilic substitution, and elimination reactions. Objectives: 1. Sources and uses. 2. Nomenclature. 3. An introduction to substitution and elimination reactions. 4. Nucleophilic substitution reactions. 5. Elimination reactions. 6. Predicting substitution and elimination. 7. Other substrates. 8. Organic synthesis and retrosynthesis. Your goals. By the end of the chapter, you should be able to name and draw alkyl halides, understand substitution SN1, SN2, and elimination E1 and E2, the reactions including the role of the substrate or the electrophile, the nucleophile or base, the solvent. Predict mechanisms and products, determine a viable synthetic route to a given target, use retrosynthesis to obtain a target. 1. Sources and uses. Sources. Halides appear in a wide variety of natural products and synthetic compounds. Uses. The structure of the molecule determines its function, and functions include insecticides like DDT, dyes, medications, food additives, and many more. 2. Nomenclature. Alkyl halides are compounds where a hydrocarbon is bonded to a halide. FCl-BrI. Recall the steps that we use to name a molecule. Identify and name the parent chain. Identify and name the substituents. Assign the location to each of the substituents. Assemble the name in alphabetical order in front of the parent chain name. The halide group is a key substituent we will name and locate. For example, 2-chloropropane and 2-bromo-2-methylpentane. Nomenclature. Stereoisomers and common names. Recall stereoisomers. If a chiral center is present, make sure to assign it R or S. For example, here is R5-bromo-2,3,3-trimethylheptane. Some simple molecules are also recognized by their common names. The alkyl group is named as a substituent and the halide is treated as a parent chain. Notice here we have the systematic name, chloroethane. Here's the common name, ethyl chloride. Methylene chloride is a commonly used organic solvent. The systematic name is dichloromethane. The common name is methylene chloride. Nomenclature, Greek letters. Greek letters are often used to label the carbons of an alkyl group attached to the halide. The alpha carbon has the halide directly attached to it. Beta carbons are one carbon down, and we can continue going, but we'll see the important ones are going to be alpha and beta. Substitution occurs at the alpha carbon. Why? Well, the alpha carbon will have a partial positive charge and the Br has a partial negative because this is a polar bond. The amount of branching at the alpha carbon will also affect the reaction's mechanism. There are 3 types of alkyl halides. Primary alkyl halides, which means only one R group on alpha. Secondary, 2 R groups on alpha. And tertiary, 3 groups on the alpha carbon. 3. Introduction to nucleophilic substitution and elimination reactions. Alkyl halides undergo substitution and elimination reactions. The alpha carbon is sp3 hybridized and has a good leaving group, a halogen, Cl, Br, or I. Alkyl halides can undergo a substitution reaction when reacted with the nucleophile, where the nucleophile substitutes for X, an elimination reaction when reacted with the base. The base pulls off H+, and the sigma bond becomes a pi bond. Consider substitution. In substitution, the nucleophile attacks the alpha carbon and the leaving group leaves. So the nucleophile subs for the X. In elimination, a base pulls off H+ from a beta carbon. As it's doing so, the sigma bond becomes a pi bond between alpha carbon and beta carbon. Notice what they have in common, nucleophiles and bases. They both have an electron source, or they're both electron rich. Why these reactions? Two main reasons why alkyl halides undergo substitution and elimination reactions. One, the halogen is electron withdrawing, creating a partial positive charge on alpha carbon, making it susceptible to a nucleophilic attack. Notice the nucleophile can attack the alpha carbon because the bond is polar between carbon and X. The halogen acts as a leaving group, and for a substrate to undergo either substitution or elimination, it must possess a good leaving group. The substrate is going to be our alkyl halide. Good leaving groups are the conjugate bases of strong acids. Recall that strong acids have pKa values that are low, and weak acids have pKa values that are high. If we consider their conjugates, the conjugates are going to be very stable, and that's why the acids are very strong, because the conjugate bases are stabilizing that negative charge. 4. Substitution reactions. A substitution reaction requires the loss of a leaving group and nucleophilic attack. There are two possible mechanisms, one concerted and two stepwise. 1. The concerted mechanism is called SN2. Involves breaking of the bond to the leaving group and making of the bond to the nucleophile at the same time. So this is a concerted mechanism. As the nucleophile attacks alpha carbon, the leaving group leaves. 2. In the stepwise mechanism, or SN1, the leaving group leaves first to give a carbocation intermediate, followed by nucleophilic attack. So first the leaving group leaves, leaving behind a carbocation, and then the nucleophile will attack that carbocation for the substitution to take place. SN2, concerted mechanism. Consider the generic reaction below, where the nucleophilic attack is occurring at the same time as the leaving group is leaving. A nucleophilic attacks the alkyl halide, causing the loss of the leaving group in a concerted fashion, or it's simultaneous. How might we write the rate law for this reaction? Well, for this reaction, the rate law will equal the rate constant times the concentration of both the substrate, Rx, and the nucleophile. We can sometimes call the substrate Rx. I also want to make sure that we know we can call it RLG, representing our leaving group. We can also call this the electrophile. So what do S, N, and 2 stand for in the SN2 name? S stands for substitution, N stands for nucleophilic, and 2 bimolecular in regards to the rate law. It is a bimolecular rate. SN2, concerted mechanism continued. The nucleophile attack the substrate from the backside. Electron density repels the attacking nucleophile from the front side. As X is leaving at the same time, the nucleophile cannot occupy that same region of space. The nucleophile must approach the backside to also allow electrons to flow from the highest occupied molecular orbital of the nucleophile to the lowest unoccupied molecular orbital of the electrophile. So we're having the nucleophile's HOMO attacking the LUMO. Proper orbital overlap cannot occur with the front side attack because there is a node on the front side of the LUMO, or a node between the CBr bond at the LUMO. How does the observed stereochemistry in the following reaction support an SN2 mechanism? Well, notice there's inversion, but if the chiral center starts off as S, and we have an SN2 reaction, the chiral center is inverted to R, which is evidence that there is a backside attack. SN2, kinetics and predictions. Recall that it is second order. The rate is equal to K times the concentrations of substrate and nucleophile. Less sterically hindered electrophiles will react more readily under SN2 conditions. Tertiary halides are too hindered to react via SN2 mechanism. Alkyl groups branching from alpha and beta carbons will also hinder the backside attack by the nucleophile, resulting in a slower rate of reaction. If we take a look at table 7.2, electrophile RPR can either allow access of the nucleophile for the backside attack or not. Methyl halides have the fastest rate of reaction because it's very easy for the nucleophile to attack the carbon. However, as soon as we start seeing more and more branching on alpha carbon or on beta carbon, the rate of reaction becomes extremely low to pretty much being negligible. Therefore, make sure that we know that the most reactive alkyl halides are going to be methyl and primary. They're pretty unreactive in terms of tertiary because it's difficult for the nucleophile to access the backside due to blocking by R groups. SN2, potential energy diagram. Review. What feature of the diagram is relevant to rationalize the rate of reaction? What feature is relevant to rationalize the thermodynamics of the reaction? For rates, we care about the energy of activation. Whichever step has the greatest energy of activation to get through that transition state means it's going to be our rate limiting step. For thermodynamics, we care about stabilities. Note that the products are lower in energy than the reactants, therefore this is thermodynamically favorable. Consider which reaction will have the fastest rate of reaction and why. If we consider SN2 with a methyl substrate, SN2 with the primary substrate, and SN2 with the secondary substrate, we see increasing energies of activation. Note they're all thermodynamically stable, but the energy activation is the lowest with the methyl substrate, which means it's going to be the fastest here. And with the secondary substrate, it's going to be the slowest. Tertiary substrates react too slowly to even measure. SN2 nucleophile considerations. A strong nucleophile is needed for an SN2 reaction. The rate with the strong nucleophile is fast, whereas with the weak nucleophile, it will be very slow. Be able to recognize a given nucleophile as being strong or weak. What are the factors that contribute to the strength of a nucleophile? Strong nucleophiles tend to have either a negative charge. The negative charge is in a very electron withdrawing group. Weak nucleophiles here, as shown, water and alcohol, tend to be neutral. So in general, anions are strong nucleophiles. Polarizable atoms are good nucleophiles. The solvent will also affect nucleophilicity. SN1, stepwise mechanism. Consider the generic reaction below. We have a substrate where we have a tertiary carbon. We have the leaving group leave, which will result in a carbocation intermediate because the leaving group leaves with the shared electrons. Carbon will have a formal charge of +1. Now that it's a formal charge +1, the nucleophile can then attack that carbocation center to produce the product. How might we write the rate law for this reaction? Well, the rate is going to be based really on how easily the leaving group leaves the substrate, where the rate then equals to the rate constant times the substrate's concentration, where the substrate is Rx. So what do the S, the N, and the 1 stand for in the SN1 name? S stands for substitution, N for nucleophilic, and 1 for unimolecular, since the rate is only dependent on the concentration of the substrate. The substitution reaction occurs stepwise, where the leaving group first leaves to form that carbocation intermediate, where the substrate is ionized, followed by the nucleophilic attack. SN1, kinetics and predictions. Recall first order, rate is equal to the constant times the concentration of the substrate. When the alpha carbon in an SN1 reaction is chiral, we obtain two substitution products that have opposite configurations at the reactive carbon, since the nucleophile can attack from either side of the plane. We can either have retention of the configuration or inversion of the configuration. Note, in an SN2 reaction, the nucleophile does a backside attack and only an inversion of configuration product is obtained. Even though a mixture of configurations is obtained in SN1 substitution, typically more of the inversion product is observed. Why? Well, the leaving group will form an ion pair with the carbocation. In other words, here's the leaving group leaving, but it didn't completely leave. That negative charge is going to still be sort of paired up with this positive charge, which makes it more difficult for the nucleophile to attack it from the same side. attack the carbocation, that is. So the nucleophile will attack at times more readily or more easily through the backside. The nucleophilic attack is unhindered here, while as on the front side, it's a little bit hindered because of the bromide ion. Inversion of configuration, product will be greater than 50%, and then retention of configuration will be a little bit under 50%. SN1, potential energy diagram. The highest energy transition state in an SN1 reaction is the formation of the carbocation intermediate. Note we will go from the reactants to the carbocation intermediate formation transition state that will have the greatest energy of activation. The second transition state has a little bit lower energy of activation. That's when the carbocation is attacked by the nucleophile. And then the proton transfer has the lowest energy of activation relative to the other two steps. For example, let's consider the substitution of a tertiary substrate in an alcohol solvent like ethanol. That's going to proceed through a two-step, stepwise mechanism. We have first the leaving group going, forming the carbocation. The alcohol undergoes a nucleophilic attack on to the carbocation via the O. Then the protonated O is deprotonated with the alcohol in the solution, resulting in the formation of the substitution product. The entire mechanism is really 3 steps, with that last step being just a proton transfer. This is called solvolysis because the nucleophile is also the solvent. Remember that when nucleophile is a neutral species, such as an alcohol, there will be a proton transfer after the nucleophilic attack. 5. Elimination reactions. There are 2 types of elimination reactions, E2 and E1. These are also known as beta elimination, 1,2 elimination, and dehydrohalogenation. In both cases, E1 and E2, an alkyl halide or a substrate behaves as an acid and donates a beta H+, which will result in an alkene. So here is our alpha carbon with X. We have a beta carbon that has to have an H. A base comes in and removes the H+ rather than subbing. By removing the H+, the sigma bond here breaks and becomes a pi bond between the alpha and beta carbon, and something is happening with X. Either it's leaving at the same time or it left first before the base took the beta hydrogen away. In both cases, the end product will be an alkene, and the conjugate acid of that base, or H base, and X- will be released. Mechanism may be concerted via E2 or stepwise via E1. E2, kinetics and mechanism. When an alkyl halide is treated with a strong base, it can undergo beta elimination or 1,2 elimination to form an alkene in a concerted mechanism called an E2 elimination. E2 elimination being concerted, that means the base will remove that beta proton, causing the leaving group and the formation of a C double bond C. So here is a concerted attack. The base is removing the H+ from the beta carbon. At the same time, the sigma bond is becoming a pi bond between the 2 carbons, alpha and beta, and at the same time, the leaving group is leaving. So we're going to have 3 reaction curved arrows. Concerted elimination is bimolecular and follows second-order kinetics, where the rate is equal to the rate constant times the concentration of the alkyl halide times the concentration of the base, where E2 stands for elimination, and it's bimolecular. In what ways is E2 elimination like SN2 substitution? Well, it's also concerted, but they're different in whereas we have elimination product being an alkene due to the elimination of H+ and X-, whereas substitution, a nucleophile replaces the X. Effective substrate, Rx or R leaving group. When a reagent such as sodium hydroxide is used, it is both a strong nucleophile, which supports SN2, and a strong base, which supports E2. In substitution, if the substrate has blocking groups or are sterically hindered, such as a tertiary substrate, the nucleophile cannot easily penetrate and attack through the backside. But in terms of elimination, the hydroxide group can function as a base and remove the beta hydrogen. A beta proton can be abstracted even though the substrate is tertiary. Therefore, when the substrate is sterically hindered, E2 elimination will occur with the presence of a strong base. Alkene stability overview, steric strain and hyperconjugation. Because of steric strain, considering trans-2-butene versus cis-2-butene, the cis isomers are generally less stable than the trans isomers due to that strain. Because alkyl groups stabilize the C double bond C pi bond via hyperconjugation, we're going to see an increasing stability with more alkyl groups. More alkyl groups, more stable alkene. So the tetrasubstituted alkene is going to be the more stable alkene compared to a monosubstituted alkene. In cyclic alkenes with less than 7 carbons in a ring, like cyclopropene, cyclobutene, cyclopentene, and cyclohexene, only the cis cycloalkenes are going to be stable. We do not need to indicate if the alkene is cis or trans unless the ring contains 8 carbons or more. Remember these stabilities. Cis isomers are less stable due to steric strain, and more alkyl groups, the more stable the alkene. E2 regioselectivity. When constitutional isomers, those are compounds with the same chemical formula but different connectivity, when they form as products of a reaction with one of them as a major product, the reaction is said to be regioselective. It is common for a substrate to have more than one beta carbon that can be deprotonated by a strong base. And so E2 elimination results in more than one alkene product. Let's consider the reaction of 2-methyl-2-bromobutane with a strong base ethoxide. Here is our substrate, and it has 2 different types of beta carbons. We have the 2-methyl groups that counts as 1, and we have the CH2 group here that counts as the second one. So this is a beta carbon, and this is a beta carbon, as well as this one, but they're the same. We can have either the more substituted alkene as a product, or the less substituted alkene as a product. The more substituted one is the one that's thermodynamically favorable. This is the Zaitsev product. The least substituted is called the Hofmann product. The 2 E2 products that are shown form with the more stable alkene, the Zaitsev product, and it's produced as the major product. The less substituted alkene called the Hofmann product as a minor product. E2 elimination is a regioselective reaction then. E2, controlling regioselectivity. The regioselectivity of an E2 reaction can be controlled by carefully choosing the strong base used. Experimental data indicates that a bulky, sterically hindered base will favor the formation of the Hofmann product, but the unhindered base, like ethoxide earlier, will favor the Zaitsev product. So here we have the unhindered base producing or favoring more the stable alkene versus the sterically hindered base favoring the minor product from the earlier. Now it's the major, the Hofmann product. Use sterically hindered bases to favor the Hofmann product. Sterically hindered bases, also called non-nucleophilic bases, are useful in many reactions. And the ones that you'll see quite often are going to be potassium tert butoxide, diisopropylamine, and triethylamine. Stereoselective versus stereospecific reactions. It is very important to understand the difference between the terms stereospecific and stereoselective. In a stereoselective reaction, the substrate can produce 2 stereoisomers as products, with one being the major product. So here is an example of stereoselective. We have one substrate producing a major product and a minor product. That's stereoselective. In a stereospecific reaction, the substrate is stereoisomeric and results in one stereoisomer as a product. So here is one substrate. It produces one product. Here's the stereoisomer, and it produces its own product. Example of stereoselectivity. Consider the dehydrohalogenation of 3-bromopentane, where 2 stereoisomers are possible. We have beta elimination of either this beta H or this beta H, but we end up getting either the major product as the trans species or the minor product, the cis, using a strong base. Using the Hammett postulate, we can actually see via the energy diagram that the transition state for the trans isomer would be more stable than the cis, and therefore the trans isomer is formed more stereoselective. Since the reaction is endothermic, recall that the transition state will look like the products more. If it was exo, the transition state looks more like the reactants. So it looks more like the products, and so the transition state here matches what we're seeing here in our major product for the trans, and then this one here is for the cis. Example of stereospecificity. Consider dehydrohalogenation of the alkyl halide below. If we use a strong base with the alkyl halide, we're going to get one product only and not the possible isomer. So this one will not be formed, but this only product here will be formed. You might imagine that it would be possible to form both the E and Z products, but only the E isomer is formed. To rationalize the stereospecificity of the reaction, consider the transition state for this reaction. In the transition state, the CH and CBr bonds that are breaking must be rotated into the same plane as the pi bond that is forming. So the only way to do that is to have a very specific geometry. There's only one beta hydrogen to be eliminated here, and it has to be in the same plane as the leaving group. In other words, the beta hydrogen and the leaving group must be coplanar. And you can see it here as well. These are the 4 atoms that must lie in the same plane, the H, the C, and the Br. Stereospecificity of E2. Visualize with Newman projections. There are 2 rotamers where the beta hydrogen and the leaving group are coplanar. One when there are anti, all the atoms in red are coplanar. We rotate that CC bond, and they're here coplanar as well, but they're eclipsed, the H and the Br. Since we are comparing 2 different rotamers, the Newman projections are a good tool to compare them. The staggered rotamer, where the beta hydrogen and the leaving group are anti-coplanar, is much lower in energy than the eclipsed rotamer. So the first one, where we have them anti and coplanar, it's staggered, lower in energy. Here, eclipsed, that means they're going to be syncoplanar, and they're higher in energy. The product resulting from the anti-coplanar rotamer is what forms. So here is our anti-coplanar staggered, elimination takes place, and we end up with this product here. Anti-periplanar. Evidence suggests that a strict 180-degree angle is not necessary for E2 mechanisms. Similar angles from 175 through about 179 degrees are sufficient. The term anti-periplanar is generally used instead of anti-coplanar to account for slight deviations from coplanarity. Although the E isomer is usually more stable because it is less sterically hindered, the requirement for an anti-periplanar transition state can often lead to the less stable Z isomer. Assuming that they all proceed through anti-periplanar transition states, predict the products for the following reactions. Note here, we want to start off with the anti-periplanar species. We have H, C, C, Br, H, C, C, Br in the same plane. When we draw in our products, we want to make sure that the bold wedges are on the same side of the double bond, and the hash wedges are also on the same side of the double bond. In our first example, R1 and R1 are going to be on the same side. R2 and R2 will be on the same side. With our second reaction, R1 and R2, because they're the bold wedges, are going to be on the same side. R2 and R1 here with the hashed wedges are going to also be on the same side. So we go, R1 and R1 on the same side with the first one, and with the second one, R1 and R2 on the same side. What if there are two beta hydrogen options? When the beta carbon has two beta hydrogens in the following substrate, there are two different rotamers where a beta hydrogen is anti-periplanar to the leaving group, and so two stereoisomers will be formed. We can have either hydrogen 1 or hydrogen 2 here that would eventually become anti-periplanar to our leaving group, and therefore we have two different products that are possible. In this case, the reaction will be stereoselective, but not stereospecific. E2 elimination will be stereospecific only when both the alpha and beta carbons are stereocenters. What about cycloalkyl halides? Consider the dehydrohalogenation of a cyclohexane derivative where the leaving group is attached to a ring. We do not have the potential then for 360 bond rotation of the atoms that are part of the ring. So the leaving group can either be in the axial position or an equatorial position, depending on whichever chair conformation we are looking at. Given the anti-periplanar requirement, E2 elimination can only occur when the leaving group is in the axial position. Therefore, in this chair conformation, E2 can occur, but in this chair conformation, E2 cannot occur. Here it is equatorial, and the first one it's axial. Rationalize the products formed in the following two reactions. One of the alkyl halides undergoes E2 elimination much faster than its diastereomer. Why is there a difference in their reaction rates? Consider the first example. In order for the reaction to take place, we would need the groups to be anti-periplanar. So since this Cl is coming away from us, and the other H here is also going away from us, the Cl here can only be a leaving group with the H that's attached to this carbon on this side. So it's going to be a slow process, and this is the only product that will form because of that requirement of anti-periplanar. In this case here, because the Cl group is coming towards us, the H group here is going to be going away from us based on how this carbon group is also coming towards us. Therefore, there's going to be two products possible because anti-periplanar requirements are going to be met with the H on this carbon and the H on this carbon here. So we're going to end up with two products. Predicting E2 products. There are many factors to consider when correctly predicting the products of an E2 reaction, and then deciding what the major product will be. Will the substrate produce several Regios isomeric alkenes? If so, what will be the major product, given that steric hindrance of the base that is used? Will the substrate react in an E2 reaction, stereoselectively, producing major and minor products, or stereospecifically, producing one product? The only way to master this material is to do lots of practice problems. E1, kinetics and mechanism. The elimination reaction of a tertiary substrate in an alcohol solvent like ethanol proceeds through a two-step stepwise mechanism. Here, ethanol is serving as a base, not a nucleophile, to deprotonate the carbocation to form an alkene. The first step is to have the loss of the leaving group in order to form the carbocation. The base removes H+ as the sigma bond breaks and becomes a pi bond between the carbocation and beta carbon, forming the elimination product. Like SN1, the E1 mechanism is unimolecular and follows the same kinetics. In other words, we end up with the carbocation intermediate. In this case, there are two possibilities, substitution or SN1, or elimination, E1. The reagent is ethanol, which is not a strong base, so E2 elimination is highly unlikely. SN2 is unlikely due to the tertiary substrate. After the carbocation is formed, it will either undergo substitution or elimination, depending on how it reacts with the solvent, in this case ethanol. So we'll have both products potentially, the substitution and elimination. E1 and kinetics. For E1, the rate is equal to the rate constant times the concentration of only the substrate. So elimination and unimolecular. The rate for E1 is the same as SN1. In both cases, the rate determining step is the formation of the carbocation intermediate. The leaving group must leave as the carbocation is forming. The mechanisms of substitution and elimination in this case both start with the same step, ionization of the substrate. Both E1 and SN1 share the same rate determining step. Rearrangements are common because SN1 and E1 reactions proceed through a carbocation intermediate. The carbocation may rearrange from 1,2 hydride or methylite shifts. Consider the example shown here. The bromide would leave forming a secondary carbocation. That secondary carbocation will have shifting take place, a 1,2 methylite shift, in order to form a tertiary carbocation. You can see here the second product. This is your SN1 product after the 1,2 methylite shift. This is the SN1 product without the shifting, and there would also be elimination products. When a primary substrate is reacted under isolysis conditions, only the product resulting from rearrangement is observed. So note, a primary carbocation would be too unstable to form, so the rearrangement will occur in order to support that positive charge when the leaving group is leaving. So the leaving group would be leaving, the shifting will be taking place, and this is the only SN1 product observed because a tertiary carbocation formed. 1,2 methylite shifts and ionization is concerted. In this scenario, the tertiary carbocation is formed, resulting in the SN1 product. Substrate, leaving group, Lg or X. The better the leaving group, the faster the SN1 or E1 reactions are. Remember, the rate determining step for SN1 and E1 of alkyl halides is the ionization step, the formation of the carbocation and the halide ion or the leaving group ion. The more stable the halide ion, the faster the ionization. So the reactivity towards SN1 and E1, the least reactive is the fluoroalkanes. The most reactive are going to be the iodoalkanes. Solvent and SN1 and E1. Experimental data indicates SN1 and E1 reactions are faster in polar protic solvent. Polar protic solvents include water, alcohols like methanol and ethanol, carboxylic acid, acetic acid, and ammonia. Protic solvents engage in H bonding and stabilize anionic species, such as good nucleophiles. Protic solvents also stabilize the carbocation intermediate, which results in the lower energy of activation and a faster SN1 reaction. So if we have a polar protic solvent, the energy of activation is lower, and if we have a polar aprotic solvent, it is much higher. Solvent and SN2. Experimental data indicates polar aprotic solvent is good for SN2 reactions. Polar aprotic solvents are those that cannot H bond. For example, acetone, dimethyl sulfoxide or DMSO, DMF, acetonitrile, and HMPA. You're shown the structures here of all of those polar aprotic solvents. Aprotic solvents may stabilize both cations and anions. However, the delta positive region is often sterically inaccessible to anions or the nucleophiles. So note, here we have DMSO as an aprotic solvent. The region of partial positive is sterically inaccessible, so the anions are not stabilized. Nucleophiles are less stable, thus more reactive in aprotic solvent. The activation energy will be lower in the reaction faster. Aprotic solvents raise the energy of the nucleophile, which then results in the lower energy of activation for the reaction to take place via SN2. So in this case, we have the protic solvent and the polar aprotic solvent. Because the nucleophile energy has been raised, now we have a lower energy of activation for the reaction to take place. 6. Predicting substitution and elimination. To successfully predict the products formed in a reaction, we can follow a 3-step analysis. 1. Determine the function of the reagent. 2. Analyze the substrate and determine the expected mechanisms. 3. Consider any relevant regiochemical and stereochemical requirements. Step 1. Determine the function of the reagent. For SN2, strong nucleophile. SN1, weak nucleophile. E2, strong base. E1, weak base. The following table is a good resource for categorizing reagents and mechanisms they will promote. E2, strong base, weak nucleophile. So sodium hydride, DBN, and DBU. The structures of DBN and DBU are shown here below. Strong base and strong nucleophile, hydroxide, and the alkoxide, methoxide, and ethoxide. Weak bases, or strong nucleophiles, your halide ions, thiols, and H2S. Weak base, weak nucleophile, water, and alcohols. These are examples that we will see quite often. Step 2. Analyze the substrate. Once you determine which mechanisms will be favored by the reagent, analyze the substrate. Assign it as primary, secondary, or tertiary alkyl halide, and then note which mechanisms will dominate. The table that you see here below is a table that is used by the authors of your textbook. It is a good table, and note how the strong base, weak nucleophile analysis, strong base, strong nucleophile, weak base, strong nucleophile, weak base, weak nucleophile is in regards to the reagent. And then our substrate, primary, secondary, or tertiary, is here on the y-axis of our table. If we go ahead and match up the two, for example, primary, strong base, weak nucleophile, is going to proceed primarily by E2 mechanism. If we take a look at the tertiary and maybe match it up with weak base, weak nucleophile, it's going to give us both SN1 and E1 products. This is one way to take a look at what mechanism will be the dominant mechanism. We can also separate the two, SN versus E. Here's an example table of that. Here's our alkyl halide or our substrate, and then here is the SN possibility. In the middle, we have a structure example to recall what a methyl or primary halide looks like. This is a methyl halide. It can only undergo SN2. If we do have primary halides that have 2 or more carbons, then it could also potentially undergo E2 if we have a strong base. Vinylic aryl halides correspond to having the halogen directly on the sp2 hybridized carbon. When that happens, we're neither going to observe SN2 or SN1. Secondary halides, we can actually see SN2 or SN1. It really depends on what our reagent is and the solvent is. So this is a little bit not shown here with our secondary. Primary and secondary benzylic or primary and secondary allylic halides. In other words, now we have a halogen on the allylic carbon. Now we would have potentially SN2 and SN1 depending on the other reagents. And solvent. Tertiary alkyl halides correspond to SN1 only, and remember this is only the SN possibility. We know it can also have E1. And then tertiary benzylic, tertiary allylic. So take a look at our tertiary benzylic. So we have this carbon here that is attached to the benzene ring. So it is an allylic position, but because it's a benzene ring, it's even more stable. We call it benzylic. But if we have any of these, the carbocations that would form would be very, very stable. SN1 would be the dominant SN possibility. Whichever table you like, you can even make one for just E reactions. You want to make sure that you understand that there are several things you must analyze before deciding what kind of mechanism to proceed with. Here is step 3. Consider regiochemical and stereochemical requirements for SN2. After analyzing the reagent and the substrate, you can say which mechanisms will occur. Then you're going to draw all the possible regio and stereoisomers. Choose a major using the guidelines you have learned. For SN2, we will observe a single product, which is the inversion of configuration of the alpha carbon. The nucleophile attacks that alpha position where the leaving group is connected to as it's leaving. The nucleophile replaces the leaving group with inversion of configuration. Step 3. Consider the regiochemical and stereochemical requirements now for SN1. For SN1, make sure that you draw the carbocation intermediate. Consider if it will rearrange. If not, then attach the nucleophile to the carbocation. If it rearranges, draw the resulting carbocation and then attach the nucleophile to it. the nucleophile attacks a carbocation, which is generally where the leaving group was originally connected, unless we have that carbocation rearrangement. If a carbocarbon is formed by an attack of the nucleophile, then two products are formed, the R and the S. Draw them both. The nucleophile replaces the leaving group to give a nearly racemic mixture. In practice, there is generally a slight preference for inversion over retention because of ion pairs. Step 3. Consider regiochemical and stereochemical requirements of E2. For E2, draw all the possible alkene isomers. Only alkenes which resolve from the beta hydrogen anti-periplanar to the leaving group can form. If a non-bulky base is used, the most stable alkene is a major product, the Zaitsev product. If a bulky or sterically hindered base is used, the least stable is the major product, the Hofmann product. The process is stereoselective. When applicable, a trans disubstituted alkene will be favored over a cis disubstituted alkene. This process is also stereospecific. Specifically, when the beta position of the substrate only has one proton, the stereoisomeric alkene resulting from anti-periplanar elimination will be obtained exclusively in most cases. Step 3. Consider the regiochemical and stereochemical requirements of E1. For E1, draw the carbocation formed from the loss of the leaving group. If it will rearrange, draw the rearranged carbocation. Then draw all the possible alkene isomers resulting from elimination of a beta hydrogen. All possible alkene stereoisomers will form because E1 is not stereospecific. The major product will always be the most stable alkene. The Zaitsev product is always favored over the Hofmann product, in other words. The process is stereoselective. When applicable, a trans disubstituted alkene will be favored over a cis disubstituted alkene. Phew. Let's now predict. Predict the products and label the major product. Let's put step 1 into practice. Analyze your reagents. We have, in terms of substrate, we have a secondary alkyl halide. It is a chiral center. We're also working with a strong base, and it's also a good nucleophile, which means we have the potential for E2 and SN2. Sodium hydroxide is a strong base and a strong nucleophile, so SN2 and E2 will be favored. We looked at the substrate. It's a secondary alkyl halide, so SN2 and E2 will occur, but E2 will dominate because the secondary substrates are still somewhat hindered and the backside attack is more difficult. Step 3. Now let's consider the regio and stereochemical requirements. For SN2, we know the backside attack will give inversion of configuration. So that means we're going to see an inversion of configuration. When the OH replaces the Br, we have that SN2 product. For E2 products, draw all the beta hydrogens that can be anti-periplanar to the leaving group, then draw the resulting alkenes. We may have to at times use Newman projections. But note, in terms of beta hydrogens, here is our alpha carbon, here's beta carbon, and here's beta carbon. We have all of these potential beta hydrogens that can be part of E2. So we have HA, which is this one here, elimination product, HB, which is this one here, elimination product. So here's our trans, here's the cis species, and HC, here is this elimination product using one of these hydrogens here. We have all the products resulting from SN2 and E2. Since E2 is a major pathway and the base is not hindered, the Zaitsev product will be the major product, or elimination of HA. 7. Other substrates, or R leaving group, can be different. There are a variety of alternatives to alkyl halides for substitution and elimination reactions, such as alkyl sulfonates. Mesylates, tosylates, and triflates are excellent leaving groups. They are also quite large, so we usually use abbreviations when drawing their structures: OMS, OTS, and OTF, respectively for mesylates, tosylates, and triflates. Here are their structures. This is a mesylate group, here is a tosylate group, and here's a triflate group. The takeaway from all of these is that they're good leaving groups. Sulfonates are such good leaving groups because they are very stable, just like halides, and they are also the conjugate basis of strong acids, which means they're stable. Note that as soon as the leaving group leaves, it is going to be resonance stabilized. Methane sulfonic acid, this is the acid that has these as conjugate bases, for example. The pKa's for these acids here, negative 1.9. For para-toluene sulfonic acid, negative 2.8. Trifluoromethane sulfonic acid, negative 14. So we're talking about very strong acids, so their conjugate bases are very stable. To derive the substrates, the sulfonates are made from the corresponding alcohol. For example, if we have an alcohol and we use tosyl chloride, an oxonium ion will form. Pyridine is going to act like a base and remove H+ from the oxonium ion, resulting in an alkyl tosylate, or ROTS. We would use the abbreviation OTS whenever we change an alcohol to a good leaving group, like OTS. Realize that we are just strapping the TS group to the oxygen of the alcohol. There is no change in the carbon atom bearing that OH group. So if we have an S chiral center, it stays S. But we have changed the alcohol, which is a bad leaving group, to OTS, which is a good leaving group. The reagents that we use are TsCl with pyridine as the base to deprotonate the oxonium ion. To use. To envision the compounds that can be synthesized from an alkyl tosylate, treat them the same that you would as an alkyl halide, because now this is a substrate. For example, if we have a primary tosylate and we react it with a strong base, we're going to get some E2 and some SN2 as our major product. If we use a secondary tosylate now with a strong base, sodium hydroxide, E2 will be our major product, and the alcohol, the secondary alcohol, will be our minor product. With the strong nucleophile strong base, a secondary substrate will mostly give E2 with a little SN2. Substrates, alcohols. Alcohols can also be used in substitution and elimination as starting materials to make alkyl halides and alkenes. We need a strong acidic set of conditions in order to do these reactions, because OH itself is a bad leaving group, but water is a good leaving group. For substitution, the mechanism will either be SN1 or SN2, depending on the substrate. Primary alcohols react via SN2, but secondary and tertiary alcohols react via SN1. So here is a primary alcohol, and under acidic conditions, we end up with a primary bromide. And water. Water was the leaving group. Here's a tertiary alcohol. In terms of mechanism, note how the alcohol's oxygens lone pair attack the H+ of HBr, resulting in water as a good leaving group here, or the oxonium ion. Water will then leave, and now the carbocation can be attacked by the halide ion, resulting in a tertiary bromide. And note, here's oxygen again, pulling off H+, releasing that Br-, and for SN2, as the halide attacks the carbon, then the leaving group can leave as water from that alpha carbon, resulting again in the alkyl halide and water. Strongly acidic conditions are protic conditions, which would favor SN1, but since primary carbocations are too unstable to form, primary alcohols will react via SN2 mechanisms, as we just saw below. Alcohols as substrates in elimination. Alcohols will undergo E1 elimination when reacting with sulfuric acid. Again, the strongly acidic conditions are protic conditions, which favors E1 for secondary and tertiary substrates. Here's our tertiary alcohol, concentrated sulfuric acid and heat, the alkene and water form. In terms of the mechanism, there's a proton transfer that occurs from the acid onto the O of the alcohol. This results in a good leaving group. The water leaves, ending up with a carbocation. Water can then act as a base, removing a beta hydrogen, or H+, and that will eventually result in that alkene when the sigma becomes a pi bond. 8. Organic synthesis and retrosynthesis. The whole point to organic synthesis is to make valuable complex compounds from cheap and readily available starting materials. You now know how to make a variety of compounds starting with an alkyl halide. And now if we have an alkyl halide, depending in which direction we go, we end up with different target compounds. In other words, we're able to convert an alkyl halide to an alcohol. We can convert it to an alkene, to an ether, a thiol, an ester, a nitrile, just depending on which reagent we use, and we talked about mechanisms from SN to E. Synthesis. To envision how a desired compound can be made, you need to be able to recall the reactions you can use. This means you have to have them memorized. You must remember these reactions. If we start off with an alcohol and use concentrated acid, we can produce alkenes. We're going to produce the more stable alkene, the Zaitsev product, more often than not, unless we have things like sterically hindering bases, tert-butoxide, then we'll get the Hofmann product. If we work with a binary acid like HBr, we can get an alkyl halide. We can make the OH group into a better leaving group by using something like tosyl chloride and pyridine to get an alkyl tosylate. And in that case, we can then have it undergo a reaction with a strong base or a strong bulky base to obtain alkenes. Retrosynthesis. When thinking about how to make something, we first think about what the finished product will look like. If we're building a brick house, we would first imagine what the house would look like. Then we would decide what bricks to use in order to make it. Organic synthesis is the same way. We look at the desired product. From there, we decide what substrates and reactants we would need in order to make it. This approach is called retrosynthetic analysis. Retrosynthesis example. Suppose we need to synthesize the following asymmetric ether, where we have 5 carbons on one side of the O and 2 carbons on the other side of the O. Step 1, let's identify a bond in the target molecule that can be made using a reaction you know. We know the CO bond can be made using a reaction that we know. So we can make this bond by an SN2 reaction between an alkyl halide and an alkoxide. And note that we have this big arrow, which is also known as a retrosynthetic arrow, and we use it to show we are thinking backwards with regards to the reaction we could do. So if we break this bond here, that means that that's going to be our alkyl halide, and on the other side with the O, that's going to be the alkoxide end. In this case, sodium ethoxide could be used with this alkyl halide here, 1-bromopentane. Step 2, draw the substrate and the nucleophile necessary for the reaction. So these are drawn already here for the first identified bond that we could break and make using an alkyl halide and ethoxide. But there's another option. Since there are 2 CO bonds in the ether, we can also envision an alternative SN2 reaction to make it. So in this case, if we break the other side instead, then our alkoxide would be the pentoxide, and then we would have the alkyl halide as our 1-bromoethane. So these are the reactants we would need. You will find that when you think backwards, you will have more than one way of coming to the target compound. So step 3, verify that the reaction you have proposed is reasonable. We have a primary alkyl halide here, which is good for SN2. If we use 1-bromopentane, and a strong unhindered nucleophile, which is also good for SN2, sodium ethoxide. And sodium ethoxide is more readily available. Step 4, draw the reaction in the forward direction. Note, we are trying to do an SN2 reaction, so we also have to consider the solvent. We want to use an aprotic solvent. So here is our alkyl halide, our reagent. This was a substrate. And below we are showing the solvent that we are using, in this case DMSO, which is a polar aprotic solvent resulting in our target. This is just one example of many. Make sure that you are practicing in order to hone in your synthesis and retrosynthesis skills.